So thank you for the invitation. It's a pleasure to be here. So yes, I'm from the other experiment. So I actually, although I say it's Large Hadron Collider, I'm going to show lots about ATLAS, not so much about CMS. I assume that if you want to know about CMS, you have your friends here that can tell you more about it. So, but still, there's a few things there. So you actually, there's this plot here that you see right at the beginning. There's a picture of ATLAS in display from ATLAS, one from CMS. So okay, so the talk is going to be a little bit about what you have heard about this Higgs boson. As you know, this was on July 2012. So on the 4th, everyone knows what happened there. Something like this. Maybe the wrong talks. Something more like that. So we found a particle, the Higgs boson, that was announced by the two collaborations. Each collaboration is about 3,000 physicists. We announced the results at the same time. It's not like we were planning that ahead of time, but you know, when we got close to have the results, we discussed with the CERN director, and this was decided to do. That was just before a conference at ICHEP in Australia. So this boson has a mass of 125 GeV, and it was a quite exciting moment, as you all probably follow, most of you will follow. So these detectors are really large. This is, as we said, 3,000 people. Give you an idea of the dimension of the detector. I point out here that is a little person. I don't know if this pointer can be seen. I hope you can see it. Okay, so there's a little person here on ATLAS, another person here on CMS. You can see ATLAS is much bigger than CMS. CMS will tell you that they are much heavier. So we kind of have these kind of discussions. So this particle was very exciting to discover. On July the 4th, we knew that we had something new. We're not 100% sure it was really the Higgs. It could be some kind of a Higgs boson. Was certainly a new particle. In 1 year, we get enough data that it was clear that we had the Higgs, and there was a Nobel Prize that was already given to this discovery. And here I'm just zooming in on what the Nobel Prize committee said. So this was given to the theoretical discovery of the mechanism that contributes to our understanding of the origin of the mass of subatomic particles, and which was recently confirmed through discovery of the fundamental particle by ATLAS and CMS. So we are very proud that, although it's not like we directly got the Higgs, the Nobel Prize, we clearly played a role on this discovery. I had to actually listen to the presentations, and during the presentation, someone asked in Swedish, there was a journalist asked something, which was, what about experimentalists? And I did not understand what was the answer, but I understood that was the question. So I got the video and told my student to translate because she knew Swedish. And so that's what she told me they said. And so the question was, the Nobel committee replied saying that this was clearly a question that was important, it was considered in the committee, but they first had to take into account the will of the Nobel and the nominations, and take into account the prestige of the prize, and putting all this taken into consideration, discussed in the committee, they agreed that to the prize that they had now. So, and it was interesting, they also pointed out that the internal discussion in the committee will be available on 50 years from now. So I told my younger student that 50 years from now I'll be about 90. So if I'm still alive, he has to come and tell me. I'll probably be in some kind of little house someplace, and he has to tell me what's going on, what happened. They also tried to make it feel like, which something I did not know, that they actually decide the prize right before they announce it. So they were late for almost an hour. They tried to make it sound like, oh, they were trying to decide on this. So anyway, this was quite exciting. So let's just now go a little bit back and quickly look at the standard model so that we are all on the same page. I assume that most of you know this. So it's made out of families. All the matter that we have around is made of up quark, down quark, neutrino. So then we have these electrons, and the electrons turns out to have this partner that is the neutrino, which has no mass. And this was all things that we knew in the 30s, like up to 1936, we had this idea of the world that everything was perfect, and then there came another particle, the muon particle, and this particle was totally unexpected. And I like to make this point because I think that we are exactly in a similar situation right now, where we have a very good understanding of the world with our standard model. There's just a few things that are perhaps missing there, and we really are hoping for a big surprise. So we kept taking data, and people with different experiments found out that we have actually 3 families, and with the increasing mass, the heaviest one is the top quark. As Mina mentioned, it was discovered by CDF and D0 in 1995, has a mass of 175 GeV, where GeV is 1 GeV is the weight of 1 proton, and so it's about the weight of a tungsten atom. So it's a very big particle, a very heavy particle, but it's also fundamental, meaning it has no dimensions. So this we know have dimensions of the order of 10 to minus 18, less than 10 to minus 18 meters at least. We don't know, so we'll have to keep exploring to see if there's any structure there. So these particles come with different charges, and the quarks have fractional charge. We have never seen them in the world by themselves. They are always connected into other particles. And then they also are, all these ones are fermions. They all have spin 1/2. One last thing is this other thing that is the color. And so quarks carry a quantum number that's called color. That's red, blue, or green. The leptons don't. So that's what really differentiates the quarks from the leptons. So this color is the charge that is going to be used to couple between the quarks and the gluons, and you will see in a second that's a strong force. And then we have the charge that is what we, as you know, couples to the electric current. So start talking about interactions. So here is the list of the interactions. We'll know about gravity. It's expected to be carried by a particle called the graviton, although we haven't seen it yet. Then electromagnetism that everyone knows is carried by the photon. So the photon has no charge, but only couples to particles with charge. The weak force, the W and Z, this is responsible, for instance, for the nuclear interactions in the sun, is for the beta decay. These are short length interactions, and therefore these particles are rather heavy. And so this is one of the important things in the standard model. And these two forces have been now demonstrated they can be coupled together, and this is called the electroweak force. And then you have the strong force that I already mentioned. So here is a proton with 2 U quarks and 1 D, and it couples to gluons with this strong force. So one of the goals, for instance, would be that we could have one force that could somehow put all this together. This is one of the goals of the field. Okay, so there goes the Higgs. So as you saw, we have different particles. We saw that we have these particles with higher and higher masses. People don't know why this is the case, why there are more mass. These particles have so many different values of the mass. We also saw here on interactions that, for instance, we have the photon, which is massless. We have these W's and Z's that are quite massive, actually, and of the order of 90 to 80 GeV. And so there is these differences. So why is that? This mystery can be solved by the Higgs mechanism. And these people here, so there was not just Higgs, it's Higgs, Brout, Englert, Hagen, Gornerick, and Kibble. And they proposed a theory in 1964 that generate the mass to the vector bosons. And the idea was that pretty much 10 to minus 11 seconds after the Big Bang, there's a Higgs field that just spreads and becomes active in the universe, and the particles are going to interact with this Higgs field. So it's not so much that the Higgs boson gives the mass to the particles, but it's the interaction of these particles with this field. The same thing as the magnetic field that is spreading all over the place. Is this interaction that then gives the mass to these particles. So this Higgs field permeates the whole universe, and so it exists even in vacuum. It has a value even in vacuum. So the particles are going to interact with these field with a coupling constant with the strength that is proportional to their masses. So you'll see a few times I'll be talking about couplings, and so that's the idea here. And this theory predicts then that there's a new particle that is the Higgs boson, and it has to exist with very well defined properties. So it has to be a scalar, and in the most simplified model have to be spin 0, has to be a neutral CP even component of this doublet, which is part of the electroweak theory. It couples to the Higgs gauge bosons like these, and to the standard model fermions proportional to their masses. So by measuring these couplings for the different particles, we'll be able to then see if the particle that we have is really the Higgs boson or not, because if it does, it have these kind of properties. Another thing we want to do is to look at the self-coupling of the Higgs to itself, and that is actually related to the mass. And since we now can measure the mass, if we understand this, it's an intrinsic understanding of the theory itself. And finally, one other property is that there are divergences in the standard model. This means that if you have a process, like in this case, for instance, a double-double scattering cross-section, if you produce double-doubles, you calculate that without the Higgs, and you just go to high energies, you'd calculate the cross-section that goes to infinity. So it grows above unitarity. So the probability of this happening is larger than 1, and so this is not possible. And by introducing the Higgs field, or the Higgs boson, then cancels those divergences, and you actually can have a cross-section that is unitary. So it's several things that you'd expect the Higgs to do. What we are going to cover is that we can do at the LHC right now is these 4 first ones, and I will mention some of them during the talk. Okay, so this is the standard model with our quarks and the leptons. We have the force carriers over here, and then the Higgs boson. So all this has been discovered since 1983, the bosons, the top 95, and it took about 40 years to do this Higgs discovery. But now if you look at this table already, and take into account the fact that I told you that these particles also carry different quantum numbers, we can make the calculation of just how many particles we have, and it turns out we have 12 leptons, 36 quarks, 12 mediators of the forces, and the Higgs. So it's about 61 particles if you take into account all these quantum numbers. So this is really large number of particles, and one starts thinking, is this really just another periodic table kind of thing where you have so many particles, and we don't fully understand what's going on. So perhaps the standard model is just an effective theory, and I mean it's clearly an effective theory, but there's something else that is underneath. So questions is why there are 3 families of particles. So is there a 4th one? As Mina told you, I spent some time in my PhD trying to answer that question, and I failed. Okay, so are these particles really fundamental, or if we smash them with higher energy, we'll see that they will break down and there is some substructure. Other questions is why such a large mass difference in the masses between the particles? We now have the Higgs mechanism, but still does not explain why the top quark is so much heavier than the U quark. It's just a parameter. So the standard model really does not provide the answer to this question. So even if you found the Higgs boson, we have this beautiful theory that is the standard model, still have very simple questions that we don't have an answer for. Okay. So let me now go more to the experimental part and discuss a bit about the Higgs. So how do we make the Higgs boson? I assume that you all know it's done at the LHC, at CERN. There's about 10,000 people involved in the collaboration. This is all the countries that work at CERN. US is a big part of this. I think it's about 30,000, is that true? Where are we? Where is it? Oh, here, yeah. 2007, yeah. Okay, 1,788, yeah. Okay. But this was in 2012. I don't know what is the number now. So one thing that is different here is that Israel just became a member of CERN. So they moved from this one box to the members. The difference between members and observers is members have to pay a certain amount of money to CERN every year. We don't have to do that. We contribute to the experiments, but directly to the experiments, not to CERN itself, to the institution. However, US does have a place in the council, and it attends all the meetings, and it plays a role on the program. Okay, so this means a large number of milestones for the LHC. I'm not going to go through all this list. I just wanted to point out that we started the first collisions in 2009. The first at 900 GeV. First collisions at 70 GeV was in 2010, and then 2 years after we had the discovery of the Higgs. So this was really quite fast up to the discovery. And when we had, which I'll mention in a second, we started, the LHC was designed to run at 14 TeV, but we run at 7 TeV, half the energy, because there was an accident early on. And really, when we started running here, we never thought that we were going to discover anything new. So it's quite exciting that we actually managed to find the Higgs. So here is the LHC ring. Over here is the Jura Mountain. There is the lake, the airport, that's CERN. And since Harvard is from US, that is not a member, we stay on the third world country building. That's my office, is right there over there. It's already in France, actually. And everyone points where their homes are, and mine is over here. So, okay, so there are 4 experiments, CMS and ATLAS. Those are the ones that really did the Higgs. And then we have LHCb that does B physics, and ALICE that has heavy ions. One of the strengths of the LHC compared to the program that we have in US is that they keep reusing their accelerators. So you see here one ring. This ring is actually injected to the LHC ring that is the 27-kilometer one. And you see a smaller one right inside the CERN site. So I just wanted to actually show you a little bit more in detail how everything happens. So we start here just with a hydrogen bottle. Some hydrogen bottle, you strip out the electron and you have the protons. We then accelerate them through a LINAC to 5 MeV. And then there's a little accelerator here that's called the booster. Accelerates them a little bit more to 1.4 GeV. Then you have the PS. And all these machines have played a role in the history of CERN in the past. And then you go to the SPS. And finally, this is injected into the LHC. Okay, so I think this is actually one very important issue relative to the problem that we have here in US. Okay, the LHC, as I said, is 27 kilometers. It's made out of a system of about 1,200 high technology superconducting dipole magnets. These have a field of about 8 Tesla. Pretty much, the field is just defined by the radius of the ring and the energy that we want. If you want a 14 TeV, then we needed that kind of field. Or another way of putting it, if the technology we have for superconductors is to create an 8 TeV magnet, then the energy we can provide is 14 TeV, if you have that ring. The ring that we are using was a ring that was already there, was the ring for LEP. And so they didn't have to dig another hole, they just put the LHC inside. On the right-hand side here, so this is the outside of the dipoles, and here is a dipole picture. You see the two holes of the beam pipe. So you have 2 beam pipes side by side. So you're accelerating protons there. So they'll just go inside of its own beam pipe. When they get to the experiments, to the center of the experiments, we'll move their trajectories so they collide in the middle of the experiment. And we have quadrupoles to shrink their cross section so that they create a collision. So in between these dipoles, we have these connections. And so was one of these connections that actually broke and I'll go a little bit later perhaps about this. But what happened was on the quench, there was current going through one of these connections. The solder joint was not done correctly. And this heat up, with the heat, warm up the helium that was around it, and the helium blew up. So you destroyed several hundred meters of the LHC. And so after that, it was decided we could not run the accelerator at that energy, and we decided to run it instead at 7 TeV. And currently we are in a shutdown to consolidate these connections and to try to now run the accelerator at higher energy. And I'll have a few slides to show you the status later on. So how do we detect particles? Here is a famous plot from ATLAS. I don't know if you've seen it, but a few of you have. That just shows how we detect each one of the particles that I was mentioning earlier. So one very easy one is this muon. A muon does not interact much with the matter, goes through everything, and we have these muon chambers outside. And if you just have a signal that goes through everything and just has a signal there, then it's probably a muon. But the detector is built out of different layers of different components that are sensitive to the matter going through it in different ways. So here we have a silicon kind of detector that can measure just charge deposit and has very high precision. Then we have another kind of technology for what we call tracking, to measure these tracks, interaction of the particles and the trajectory of the particles. Then we have a magnetic field that makes curve the tracks, and by the curvature we can measure the momenta. Then we have here a calorimeter, and the calorimeter, the electromagnetic calorimeter is the first calorimeter where you have less mass, and there you'll have where you can detect your electron or your photons. A photon, because it doesn't have any charge, will not interact with the early material, so it doesn't have any track here and just a little bit of energy in electromagnetic calorimeter. If it's an electron, you're going to look exactly the same in electromagnetic calorimeter, but it has a track pointing to that electron. In hadronic calorimeter, the other layer, now here that's where the protons and the neutrons are going to die, and all the other kind of heavy particles made out of quarks. And so you see a proton as charge, it will have a track and then dies over here. And the neutron has no track, and you'll just see amount of energy deposited in the hadron calorimeter. And the muon, I already said, is the one that goes through everything and just gives a sign over there. So over there should be anything else, just the muon. And then we have this dashed line here, that's the neutrino. So the neutrino, I told you there is no charge. And so the neutrino can just go through all the detector and does not interact with anything. And we just cannot measure it. So the way to measure the neutrino is by measuring everything else in a transverse plane. And once we measure everything else, you subtract that. So we are supposed to have in a transverse plane, if there was no neutrinos, then the energy should balance out, and you should have conservation of energy in the transverse plane. So if a neutrino is there, then it disappears, you are having some missing energy in that direction, or missing transverse momentum. So you add everything else out, and what remains is the neutrino. Okay, so if we put this now, look at the ATLAS experiment in a different graph. These are the different layers that I was just showing you. What is spectacular about ATLAS is these muon detectors. Where I'll show you some pictures. This is a toroidal magnetic field, so the field goes around the detector like that. Particles are going to bend in the z direction, which is this one here. And there's another toroidal field here. And these are the different layers of the detectors that I've shown you. And I don't think I'll go into much detail into all this text here. You can, if you ask, I can then tell you. But it's interesting I should probably mention that for the muons, the resolution of these measurements is of the order of 50 micron. And the size of our detector is 25 meters high. So you measure 20 micron within this huge size. So yeah, so the detector is about 3,000 tons. There's lots of cables, about 3,000 kilometers of cables. So one thing is, why does this need to be so big? And pretty much has to be big because we want to absorb the high energy particles. So you need to have large volume and lots of material there. We also need lots of independent channels so that we can track with precision all these particles going through the detector. And you need things of the resolution of 10 micron. And so that's what is inside here in the center. And also we need this to be very, very fast. So we need the detector to run so that he can detect the data that happens 40 million beam-to-beam crossings per second. And you need your detector to be able to capture that data. And since we don't have computers to store all these 40 megahertz data, then we have to reduce it to something like of the order of 200 hertz, 200 events that we actually store on tape. So here is the picture that I showed you earlier. It's a very famous picture. Now you can probably see better what this is. This is the toroidal magnet. Down here you see the calorimeter, and this would be the magnetic field, and that's one of the muon chambers. Another picture that is not so famous is this one. That's the other toroidal field, the toroidal magnet. So here are the coils, and the field will be like that. So this is inside the cryostat because it's superconducting material, so you have to have it in vacuum and cooled down. It's a very big and heavy thing. So is it traveling to ATLAS? There's 128 wheels on this truck, and it took like a day to go pretty much from my office. It was built next to my office to the cavern, which is a kilometer or something like that. Okay, another picture of what I think is probably the most impressive thing. Perhaps I'm biased because I work on this, but is these big wheels. So 25 meters high. They are actually, so these are the end caps. They are on the edges. These guys were built on the wall and then moved into the detector. They are hanging from 2 points. If you go to this huge thing and you touch it, you'll just move. So it's quite impressive. So this was built finished in 2007. And I think we always like to point out there's about 30,000 tubes on these detectors here. So they are filled out of gas, and they're very thin with a wire inside. And out of 30,000 tubes, we managed to only have 16 dead. And the last piece of the detector that was put in is this small wheel. This was actually built at Harvard with this detector, with these chambers, and you can see it coming down. And this picture could be the same picture I'm showing you for what's happening right now, because this detector was removed. Right now we are in shutdown, and we removed the detector up. And we have pictures exactly like these. We don't know if they are from 2008 or if they are from a few months ago. Okay, and finally, last picture is myself over here. I don't know if it's to show that I'm too small or if the wheel is too big, but you can see that, me and students and postdocs right next to the wheel, and so as you can see, this is very, very big. Okay, so to produce the Higgs bosons, we need to collect as much data as possible. One thing that you will hear in the talk is this luminosity thing. So that's just how many events, how many collisions can we produce inside the detector per centimeter square and per second. So the larger the luminosity, more collisions are happening, more events we are going to have. So that's the equation for the luminosity. Pretty much depends on the number of protons you have in bunches. So these protons are coming in bunches. There's about 10 to the 11 protons in each bunch. You bring them to collision. You squeeze them to a small cross-section. So the cross-section of these bunches are down here. You make these numbers as small as possible. You make as many as possible protons inside of the bunches. And I try to have as many bunches as possible. So the machine is running at 50 nanoseconds right now spacing. We're going to run later at 25 nanoseconds. So we'll increase the number of bunches by a factor of 2. And then you try to just go around as much as possible. Okay, so this is the number of events that we produce. I have this luminosity number. I multiply by my cross-section, and I get the number of events for each process. That's the luminosity versus time. So when you heard about the Higgs discovery, we had taken this much luminosity here. Since then, we collected way more, so that's all this data. And those are the results that I can show you today. Okay, so one last thing is one of the challenges, the biggest challenge in 2012 has been the PyLab, because we try to have as many events as possible with squeezing the beam as much as possible. We just start having lots of events happening at the same time, and we have this thing called in-time PyLab and out-time PyLab. How many events do we have at the same time? Something like, on average, 20 events. That each time a crossing happens, there's 20 events, 20 things happen, and we need to identify our Higgs out of that. Maximum number is about 35 events happening. So how bad does that look? Here is an example that's an example with 25 collisions at the same time, and we need to pick the one that we are interested. So this is an event, it's a Z boson. So you know, it's a similar particle like the Higgs, but here it goes into 2 leptons. In this case, it was 2 muons, because you see here there's a signal in the muon chambers outside of the old detector, and inside this is the tracking, and you see it's a mess, right? And here you see all the different vertices, and we have to identify that this Z was produced on this collision. Everything else here I don't care, so I have to eliminate all these tracks. I really only care about these 2 tracks coming from that collision. So that's kind of the game. And the other thing is, so we have this big detector, I told you, 25 meters high. Collisions are happening in the middle. So even if the particles move at the speed of light, they are not going to cross the detector for one collision. When the second collision comes, the particles are still crossing the detector, and they are still half the way. So if a collision happens here, when I have another collision, the particles will be something over there. And if I have another collision, the particles will be something over there, and so forth. So I have these signals accumulating in my detector, and I have to be able to identify them and to point to the right collision crossing. So those are 2 of the major challenges that we have to handle. Okay, how many events we have produced? We have about things like W bosons and Z bosons of the order of the millions. You have 400,000 top events that Mina also mentioned, and the Higgs candidates about 600. And we needed to do all this physics here to study these events before we could go to the Higgs, so that we could make sure that we actually understand our detector. And so there's about something like Higgs produced every 50 minutes at LHE, I believe, at the luminosity that we award at the end. So let's go back to the collisions. Think about your protons. We were saying, oh, the protons collide with each other. In reality, the protons are made out of quarks, and they have gluons there. What collides is the quark of one proton with the quark of the other proton, or the gluon with another gluon. And we need to, for the Higgs, we need to know if this is a quark or if this is a gluon, and now actually, what is the actual proton that is interacting. So we need to know this with precision, and there's been a program at the LHC to measure these with high precision, started from the beginning. For instance, one of the ways we do that is we measure the W and the Z cross-sections. That's the plot from CMS, showing the cross-sections versus the center of mass energy. Here is a 70V and 80V. And one thing is, if you measure the W plus or the W minus cross-sections, they will be different at LHC, because we are generating these Ws with protons where there are 2 U quarks and only 1 D quark. So we're going to have more W pluses than we have W minus, and that's what we observed. And by using this kind of information, we can determine what is called the pattern distribution functions, and that is fed back to the theorists that can then tell us what is the theoretical cross-section for the Higgs that we expect. And this is one of the major uncertainties on the actual cross-section of the Higgs. So we have measured many different processes before we go to the Higgs, and things all agree very well with the standard model within the uncertainties. And these cross-sections are actually of the order of the cross-sections of the Higgs. And if you think about how that actually works, this is a plot where I put the time of the discoveries from ATLAS on this right-hand side, or the measurements, sorry, on this right-hand side. And here, the time for the measurements at the tevatron. And the lines are different processes, cross-sections of different processes. And so the LHC is this line over here. So that's when you so this is the total cross-section, this is the big cross-section. Then you have Z's and W's over here. And the Higgs sits down here. So we went through all this process in about 2 years, 2.5 years. And if you can compare that with happened at the tevatron, that was about 20 years of research. So everything was really, really very fast. Okay, so what have we seen to believe that we have the Higgs boson? So to produce the Higgs boson, remember we said the Higgs couples with the proportional to the strength. The strength of the coupling is proportional to the mass of the particles. So you want the Higgs to be somehow to produce some heavy particle, and then from there you'll decay into a Higgs. So the heaviest particle we have is the top quark. The top quark does not exist inside the proton, so somehow, but you can produce them by this kind of diagram. You have two gluons, they make a triangle with top quarks, and then that decays into the Higgs. Another way is this kind of diagram, which you call vector boson fusion. And here we have the two quarks that come from the proton. They will exchange a vector boson, like a W, and then this W is a heavy particle interacts with the Higgs, and there you have your Higgs. So you'll look for a Higgs particle decaying into some different things, or you look for a Higgs particle with extra two jets. And then the Higgs will decay. The Higgs can decay. You're always going to try to decay into a heavy particle, so you can decay into BB bar, decay into Z's, and then the Z's decay themselves into leptons, or you can have the Higgs decaying into photons, but it cannot go directly to photons because there's no charge. So it goes through some triangle. For instance, here we have some W's, a heavy particle again. Okay, so now the game at LHC since we started was to explore this chart. We did not know where the Higgs was, so we had to look at possibilities of the masses of the Higgs. And so what this chart tells us is the production of the Higgs at LHC, the cross sections with different kind of the modes that I was telling you. Now, after this time, we know that it's at 125, so we know that we are right here. So the major production is this gluon fusion that I told you. Second one is this other one here, and then there is these other productions where you have a W and the Higgs, or a Z and the Higgs produced. And that's this diagram. And finally, you have this diagram where you produce the Higgs with two tops. Okay, so this is the very final thing that people have just recently tried to measure. Again, we have been exploring the branching ratio. So how the Higgs, this is how the Higgs decays. So the Higgs can decay into many different things depending on their mass. That was the plot that we tried to explore. Now we are at one very specific point in the plot, that this line at 125. So the Higgs will decay mostly into BB bar, then into WW, then into gluon, but that's impossible to see because there's too much background, then so forth, okay? So we're just going to go quickly through these different channels, and I'm going to show you these plots, so you'll see them on the left-hand side just to help you guide the eye for each one of these channels, okay? So golden channel, that's how the LHC initially we thought we would build is like, there's such a big mess that can happen with all these protons. You saw those plots with so many tracks. We don't know if you can even identify things there. But let's make sure that if we cannot see anything else, at least we can see muons. And there was this one channel that is two Z's. The Z's can go into muons. So if we produce a Higgs, it for sure will be seen on this channel. Also gives you a very nice peak. So that's what people call the golden channel. So here is a picture of it. These are the muon chambers, one muon here, another muon in the forward chambers, and two muons over here. So for mu, there's a transverse picture of the event. For muons, we reconstruct the masses, and it seems to be in the Higgs mass. This is with the electrons. So here you see, now it's inside more of the detector. You see these energy deposits in the calorimeter, 2 energy deposits here, another 2 over there. So we identify these as 4 electrons. They all come from the same vertex. You see lots of other stuff here, but we want everything from just this one vertex. And so we say, well, this is another Higgs. And this is what we had in at the time of the discovery, both from ATLAS and CMS. Here is the little peak from ATLAS. Here is the little peak from CMS. And you see the number of events, right? This was really not so many events, right? But the fact that we put all the channels together convinced us that we had something there. But that's what we had. So now what we have is something like this. This is the peak for the Higgs. The red is the background from the standard model processes, something like this. And now you can see really very clear a huge peak. In the green here is the subtraction of the background from your total number of events. So if you subtract the background, you just get the Higgs peak, and so that's what we have. So we, in ATLAS, see a little bit of excess on this channel, but we have a very clear peak there. We do now the same thing for the gamma-gamma. So we saw already how the Higgs to gamma-gamma goes. It goes through these vertices. So the gamma-gamma is down here. The cross-section is very low, but the branching fraction is very low, but it's a relatively clean signature. It's going to give you a very well-defined peak, and you can see it on the top of a smooth background. And the photons are stable particles, so we will identify them immediately. So here are 2 photons in the CMS detector, and so this is reconstructed to be a candidate to be a Higgs. Okay, so that's the picture from ATLAS when we discover it. This is the peak from the Higgs. Let's just focus on the first top, which is the first plot, which is just the raw data. This is a bit massaged. So you see a smooth distribution. That's the backgrounds from all these processes. If they add them all together, it's just a smooth curve. We fit with a polynomial, get rid of those events, subtract them. That's what you see here. The excess is the Higgs. So you can see now very, 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 very clear signal. I was, oops. Yeah, so okay. So that's now with the current data, and exactly same thing, and you see here the excess. So at the peak of about 200 events of Higgs. Okay, double W. So this is an interesting channel. So these are 2 Ws. The Ws go to a lepton and a neutrino. So you'll have missing energy from the 2 Ws, and you just have 2 leptons and nothing else. So I told you I can reconstruct 1 neutrino. I can, because I measure everything else. But if I have 2, now I have a problem, because they have 2 neutrinos. I don't know which one has which momentum. So this becomes much more complicated. So we lose the possibility of having a nice peak, and so this channel is quite difficult to measure. However, the channel was, and you'll see the signal growing here, the channel was the one that had a broader range that we could find the Higgs. So if the Higgs was 140 GeV, this would be the channel that we could find. It turns out, because the Higgs is 125, that the ZZ channel is the one, or the gamma-gamma channel. So no one knew which one was the right one to look at until we actually until we found it. So you see here, the large blue thing here, that's the standard model double-double production, which is very interesting by itself, especially this diagram, where you have a coupling of 3 bosons here. But on the top of that, you see the Higgs, and you see that it's a very broad signal, pretty much on the top of this very broad background. And turns out that this plot is different from all the other ones. On the subtraction here, we are subtracting the signal also, so you don't see much of an excess. But the excess on this diagram is quite significant. So if I put everything together, I measure I now ask the question, how much, these events that I show you a bunch of peaks, how do these amount of events I've seen compare to what I expected if this was a Higgs? Okay? And so that's what this plot is telling you, and that's the ratio mu. And as this ratio here. And so if what we observed is what we expect from the standard model, then this ratio should be 1. And then we have the standard model Higgs. If it's different, then it will be something else. So here you see the 1, the ratio. You see gamma gamma, ZZ, and WW. And so we see that in ATLAS, we see more in this channel gamma gamma and ZZ than we'd expect from theoretical prediction. But not, there's big errors here. WW is right on the mark. So when we combine, we are a little bit high. Now, don't get too excited here because CMS measures less. So there's not really kind of a reason to think that we have an excess of events. I think I'll skip that. So, okay, so what about fermions? So we mentioned that it was very important that the Higgs couples to fermions and they should be proportional to their masses. So what can you say about fermions? Turns out fermions are more complicated. So here are an example for taus, where you see the branching fraction is here, but taus are much more difficult to identify, and you also have large backgrounds. So here is one event where a tau decays into 2 leptons, and then you have another tau, 2 taus decay hadronically. So taus have many different ways of decaying, and which makes the analysis very difficult because you have to make all these possibilities. So this is the signal as we have it right now. All these colors are the expected, all the backgrounds predicted. The red is what we'd expect from the Higgs. The black is the data, and you can see that we have a little bit of an excess, and that is consistent with the Higgs of a mass of 125. He's speaking about the same place. Of course, the statistics is not very large, but it's some indication that we do see something in the tau channel, and this is about a 4 sigma observation. For the B's, that's even more difficult. So the B's, the cross-section is the branching fraction is the highest because they have heavy quarks. However, there's lots of background, so we have to go to production mechanisms with other particles like the W Higgs. The cross-section for that is much smaller. So we have few events. We have to place strict cuts. This is the kind of thing we have. This peak is actually mostly background, and the signal would be this little pink thing here. So there's not much there for us to talk about. And so these are what we measure when we turn these events that I show you, we turn them into how does this compare to the standard model prediction. You'll see that ATLAS pretty much measures something on the BB bar that is non-existent. It doesn't see much of a Higgs there, but you can see the errors are huge. And for taus, it's a little bit above what we'd expect. Okay, so now we have to put all this together. So we have all these couplings, because the couplings just come from each one of the channels. So we have all these things that I can now put in a big fit and try to see how is all these things consistent or not with each other. And this is a plot that shows how does the channels, for instance, this is ZZ channel, this in blue, in red is the gamma gamma, in green is the WW. How does these measurements, independent measurements of the mechanism of production of the Higgs by here called vector boson fusion. So some things where we have the Higgs produced by complicated diagrams like this one or this one or this one, comparing those without the Higgs is produced by gluon fusion. Sorry, actually this is gluon fusion and TT bar. So it's these two compared to those two. And we try to compare those things and see if the rates that we see from the different diagrams are consistent with the standard model. So the standard model is right here. Now you can see that the errors are very big. So this is all more or less consistent. And here is another type of diagram we look at, for instance, to see if the couplings of diagrams like this one where the Higgs goes to gamma gamma with a triangle, is an agreement with the standard model with also the production one, where the Higgs is produced with the gluons through a triangle. The triangles are quite interesting because if you have new physics, and that's why people are very excited if you have a gamma-gamma, something like, if you have an excess in the gamma-gamma, it will be quite exciting because if you have new physics, you could have a new particle in these triangles that are very heavy. So if we measure the Higgs cross-section in the gamma-gamma to be just what the standard model predicted, then it means that there is no other particle that couples with heavy particle coupling with the Higgs in these loops, which is a little bit sad. Okay. Okay. One little detail. Actually, when we measure the mass, right now we are measuring it with more precision. Turns out that in ATLAS at least we have a measurement that when we measure the mass from the different channels, if it's the ZZ, we're measuring a little bit low. If it's in the gamma-gamma, it's a little bit high. So there's some speculation. Of course, it could be two particles, but that's not really the case. Because first of all, CMS doesn't see that, and it would be very difficult to explain that. Of course, the reason, most likely reason is just that there's a statistical fluctuation. And so the standard model result will be something in the middle over here. Okay, so I think actually I'm probably going to skip a couple slides. So first one, I just quickly to tell you that we also look at the spin of the Higgs, and we measure the angle distributions of the particles, and from there we try to estimate the spin. If it's a spin 0, should be a flat distribution is variable, which is a cosine of the angles in a Higgs rest frame. We do that, and we are pretty convinced both in the ZZ channel and the gamma-gamma channel that the particle is a spin 0, is a CP even state. So it's not a spin 2 particle, for instance. So we can now put the Higgs together with the standard model and see how everything fits together. Even before we looked at the data that we have from the LHC, here is the letter weak fit. So we put all the standard model data that we know, we fit it with the knowledge we had from the Tevatron, which had already excluded some region over here. We fit that, and before the LHC, this fit was telling us the mass of the Higgs was 125.2. Granted, it was in between this tunnel, there's not much space in between those two things, but it's kind of funny to see that he actually had 125 there. And now we have much more information. We have the Higgs. So here we're going to compare the mass of the top and the mass of the W. And you see the white, the big thing is what you predict if there is from these feeds without the Higgs, and the blue is when you have the Higgs. So if the standard model, if there's only standard model and all the physics we have, then all these points will agree, and it's kind of what's happening there. So that they have to measure this with much higher precision. So one of the things we will want to do is measure the mass of the Higgs with high precision, mass of the top with high precision, and try to shrink this to a small point, closer than and different from the Higgs. Okay, so on the next. Yeah, so I'm just about to close, and I wanted just to mention a few things about what's going on now with the LHC. So we are in the shutdown. This is a very recent plot from the status. So probably let's just focus on the LHC. So there's different machines, as I told you, we closed. They've been doing things to make the machines ready again. The idea is to start in 2015. That's what the green thing here is. They'll start with beams in January, but they have to get the commission the beams, so data will start at the end of March, beginning of April. Okay, so they are over here on this red arrow, and they'll have to start powering everything and get it ready to go in December, and then they'll start in January. So the goal is to start with about 13 TeV. That seems like the machine was settling on, and there's going to 25 nanoseconds bunch crossing, so they will have the luminosity could be a factor of 2 larger. There are other issues there, but we will have a much higher rate. So we expect a larger maximum luminosity eventually once the machine is fully commissioned, and we'll have 300 inverse femtobarns. So about 10 times more data. So they're going through a very complicated process to get all these things working. In particular, they have these splices. They are fixing these these connectors that I mentioned to you that have the problems with the solder joints, so they're fixing these solder joints. And the numbers that they have to fix is like of the order of, there's actually 3,000 here. So there's lots of work they had to do. And and so, yeah, so they have to actually fix one of these things. It's one every 3 minutes, the number of things they had to do. So a very large number. And this is the status, so it's mostly complete. This is all the fixing of the splices up here and installation of new quadrupoles and dipoles that had problems. These are all complete also. So they are in very good shape towards being ready for starting. And here is a graph showing the status. The blue is what was the plan. Red is what we have done so far. So they are 2 weeks late, but that's actually pretty good in this kind of project. And they plan to, now they're going faster, so they plan to actually achieve the goal. Okay, so just to finish, for future, this show you what we're going to do with 300 inverse femtoborns for the different channels. We're really going to try to measure all the couplings I was telling you with much more precision, including things that we don't have any precision to measure right now, like Higgs to WW, TT bar Higgs, Higgs to mu, sorry. So is a huge range of things that we can do, and then we're going to try to make these kind of graphs where we measure the couplings, and you expect them to be linearly related to the mass of the different particles, and they're supposed to fit like that. Okay, so there are lots of other questions that we can answer with this data at the LHE. I mentioned several of these ones here already to you before. So it's not only the Higgs, but there's other questions that we would like to address. What I think is that most interesting is there anything unexpected that we could find? Like the muon case that I mentioned earlier, there's been different situations in physics where we actually, and in science where we actually had an unexpected surprise, which I think that's what we'd like to look at. I have a little story here that I'm going to skip. And so to finish, we had the first proton-proton LHE run, which I think was exceptional. Was very fast getting data out with beautiful data. The machines and experiments, they worked very well. And so I think everything was behind the expectations that we had at the beginning. We did the rectification of the standard model. Not only we measure everything, which I did not mention here so much, but we measure all the standard model particles, as we saw in one of the graphs. We found the Higgs boson. And so in some sense, this was really kind of the final point of the discovery of the Higgs, of the standard model. And as I show you right quickly, we are doing this shutdown, but sounds like we're going to be ready to start taking data again in 2015. Okay, thank you very much.
Thank you for a very nice talk. Questions?
Okay. So you get these thin in the angular distribution, but how about how do you know if this is scale of a pseudoscalar?
How do I know that it's a scalar rather than a pseudoscalar? Well, first it couples to photons. So I don't know if you actually maybe set.
You can also do the same. Do the scalar versus pseudoscalar hypothesis from the ZZ, right? Z to 4n. Isn't it?
Yeah.
So you can from those.
6 angles.
Yeah, it's also from the
Yeah.
angles.
So there are many different. So there are many different hypotheses you can check actually for angular hypotheses, and every time the scalar one wins. with some probability.
So pseudoscalar.
Definitely ruled that, yes.
Both ATLAS and CMS. have
But
done
yeah.
Yeah, both ATLAS and CMS have done that.
Yeah, I think I actually have one slide someplace on the book.
Any other question in the meantime? Yeah.
You mentioned that the decay product of the Higgs two particles have the mass, the Higgs each. Have they been observed on the way up in the energy scale while searching for the boson?
Sorry,
Half the energy?
which part? I'm sorry, I didn't get the question. I didn't get the question.
The decay product
Uh-huh.
of the decay of the Higgs,
Of the Higgs?
you pointed out, are two particles, each half the mass of the Higgs.
Not quite.
Well, that's
So for instance, Higgs
your
to
statement, excuse me.
Which,
no, so the Higgs decays into different kind of particles. It can decay into 2 photons, or it can decay into 2 Z's.
But they are half of the energy. Have they been observed in
Yeah,
the
the
search
Z.
for the boson when the energy reached half
Yeah.
the value of that of the boson, of the Higgs boson?
yeah, so the Z and the W have been,
Yes, so all these particles that I was talking about here, so for instance, here you have a Higgs goes to a gamma gamma, so these photons have been observed before, or you have the,
Could be a very much cheaper way to estimate the number of Higgs bosons. If one could.
these particles,
The decay product.
but these particles, for the Higgs to be bar, so these 2Bs can be produced by many different mechanisms, many different ways. So to be able to identify that it comes from a Higgs is very, very difficult because it can be produced by so many different ways.
any other questions? Dave?
Guimaraes said that from CDF, after the top discovery, you were looking for physics beyond top, like additional quarks. So now after the Higgs discovery, what physics are you interested in looking at beyond the standard model?
Everyone asks the same question. Well, so, I think that, I still think that at least at the beginning, the ideology, the Higgs is still interesting to study. I certainly am interested on finding any kind of new physics. I'm not so sure if it should be supersymmetry, which is the other question that everyone asks. So I don't think I want to just go and look for one type of supersymmetric model or something like that. I think I prefer to look at some signatures that will be sensitive to some possible new physics, but not necessarily to follow a specific model. So, for instance, I'm interested in double scattering. And, if there's some new physics that would produce multi-leptons, then it could be founded there. That's one. I prefer that than an approach where I'll just go look for a specific model. But if you ask me what do I think that's going to happen, I don't know also.
No. Thanks. There was a question in this area, right? No? Okay, earlier. I think. Never mind. Okay, any other questions? No? Let's thank Joao for a very nice talk. Thank you.